Good morning to everybody. I welcome you to today's webinar. It's concerning the characterization of thermoelectric materials. Let me start first with some organizational information. So all participants are muted, so you can't interact with me by audio, but you can type comments in the question and answers section tool during the webinar. These questions will be answered at the end of the presentation. This webinar will be recorded, and the recording can be found in the chat after the webinar. And your comments, your feedback after the webinar will be highly appreciated. So this webinar concerns thermoelectrics, an overview over the topic thermoelectrics and the instruments which are concerned. So my name is Hans Marx. I'm application specialist and area sales manager. I studied chemistry in the University of Aachen. Sorry that I interrupt. Sometimes there are more attendees coming in. Sorry. So I'm working for Linzai since more than 12 years, and my spoken languages are German, English, and French, so that you may type in questions or write emails to my address in these three languages. So, for those who do not know our company yet, Linzai's Messgeräte is a German company situated in Selb, founded almost 70 years ago by Dr. Maximilian Linzai, whom you can see here on the left-hand side. His son, Klaus Linzai, took over the company. He's the owner of the company, and the CEOs are the sons of Klaus and grandsons of Maximilian Linzai, Florian and Vincent Linzai. Linzai manufactures in Selb in Germany and has own sales and service locations in the USA, in China and India, and distributors in more than 65 countries worldwide. Beside the manufacturing of instruments, we do service measurements in our application labs. And in the beginning, we started to build up data loggers and flatbed recorders for the data acquisition of the thermal analysis instruments. These is no more manufactured. All data logging is done by computer, obviously. So today we manufacture instruments for thermal analysis to measure thermal conductivity and to characterize thermoelectric materials. So we manufacture differential scanning calorimeters for the measurement of melting points and phase transitions and chemical reactions, thermobalances to monitor chemical reactions, so-called simultaneous thermal analyzers, which do thermogravimetry and calorimetry in one instrument simultaneously. We manufacture thermomechanical analyzers and dilatometers for the measurement of length change variations. We manufacture instruments to measure thermal diffusivity and conductivity, analyzers to analyze thin films, the Hall effect, and we do a lot of customizations, so special instruments for very specific applications, which are built according to the needs of a customer. But today's topic is thermoelectrics, so I will present analyzers for thermoelectric materials. So The agenda is, I will start with the basics of thermoelectricity, mention the Seebeck coefficient and the figure of merit, show you our product line up for thermoelectric applications, and will close by application examples in this field. And at the end, we will have a question and answer session. So what is thermoelectricity? Thermoelectricity describes the direct conversion of the temperature gradient into electricity and vice versa. So this means that without any moving parts, the temperature gradient is transformed in electricity. The thermoelectric effects are named to three persons, Seebeck, Peltier, and Thomson. Thermoelectricity may be used, for example, for the recovery of waste heat. So whenever you have a hot exhaust pipe, for example, you may transform this temperature gradient directly into electricity. Thermoelectricity may also be used to power as an autonomous power source and to power self-sufficient sensors. So the Seebeck effect describes that a temperature difference creates an electrical potential. So if you have a thermoelectric material, you heat it on one side and you cool it on the other side, you can harvest a voltage and measure voltage on it. And the Seebeck coefficient is this voltage between the high and the cold side and the temperature difference between. So this voltage is a response to the temperature difference across a material. It's measured in volt per Kelvin or microvolt per Kelvin. And the highest Seebeck coefficients are found for semiconductors, which may have Seebeck coefficients of hundreds of microvolt per Kelvin. Metals are much poorer thermoelectric materials. So in general, to characterize the performance of a device, system, or method, the so-called figure of merit is defined. So this figure of merit compares or allows to compare the relative utility of a device material for a certain application. It's defined for thermoelectrics as the figure of merit equals the so-called Seebeck coefficient squared multiplied with electric conductivity and divided by the thermal conductivity. So the aim to have a powerful material with a high figure of merit is to increase the Seebeck coefficient, to increase the electric conductivity, and to decrease the thermal conductivity. The figure of merit may be measured either by measuring Seebeck coefficient, electrical and thermal conductivity, and do the calculation according to this formula, or there is a method, the so-called Hamann method, which allows to determine directly the figure of merit. We'll see later on a later slide how this can be done. Once you found a good thermoelectric material, in order to make use of it, so-called thermoelectric modules or thermoelectric generators are built up. In these generators, you combine P and N type thermoelectric materials. Put them either between a hot and a cold side and harvest the voltage. This is a thermoelectric generator, or you may use it as a Peltier element by powering it by an electrical current and get a temperature gradient, so meaning a cold side and a hot side. The conversion energy efficiency can be calculated by this formula integrating the figure of merit. or it can be calculated by the power output generated by a certain thermal power input. So instruments, we manufacture a couple of instruments to characterize the materials of this so-called legs of a thermoelectric generator. Those are the thermoelectric materials. And other materials used to build up the thermoelectric generators or even the complete generator. So there are instruments like the thin film analyzer or the thin film laser flash analyzer to measure the thermal conductivity and other thermophysical properties of thin films. There are instruments like the laser flash analyzers, the so-called LSR, Linzai Seebeck and resistivity instrument, or the LZT meter to characterize thermoelectric materials. The thermoelectric generator tester, the TEC tester, allows to measure, to characterize the complete thermoelectric generator, and DSC analyzers may characterize the materials used to build up a thermoelectric generator. So Linzai offers a very broad product lineup for the characterization of thermoelectric materials, for bulk materials, for thin films, and this in the very broad temperature range, from cryogenic temperatures up to plus 1,500 degrees centigrade. The figure of merit depends on temperature, and not only the figure of merit, but also the Seebeck coefficient, the thermal conductivity, and the electric conductivity are all dependent from the actual temperature, so that the characterization has been done at a defined temperature. So let's have a first look on the first measurement method. It's a so-called LFA, laser flash or light flash analyzer, working according to this American standard. The principle is the following. You send a short energy pulse, a light flash or a laser pulse to your sample, and you measure the temperature increase on the rear side of the sample by an infrared detector. The infrared detector registers a curve, the temperature rise on the rear side of the sample versus time. And from this curve, the so-called thermal diffusivity can be calculated. And by multiplying the thermal diffusivity by the heat capacity and the density, sorry, this is a thermal diffusivity, this is the density and the heat capacity. By multiplying these three parameters, you get the thermal conductivity, which is used to calculate the figure of merit. Additionally, the Seebeck coefficient and the electric resistivity has to be measured. This is done by the so-called LSR machine, LSR standing for Linzai, Seebeck, and electrical resistivity. In such a machine, the thermoelectric material is placed between two holders, one of them containing a heater, so generating a temperature gradient throughout the thermoelectric material. And from the side, you have temperature probes and voltage probes measuring the voltage drop and the temperature difference. And by dividing this voltage by the temperature difference, you get the Seebeck coefficient. In the same machine, in the same setup, but in another measuring mode, you may measure the the electric conductivity. Again, the thermoelectric material is placed between these two holders. In this mode, an electrical current is fed through the thermoelectric material. By knowing this electrical current, the intensity of the electrical current, measuring the voltage drop over the material, And knowing the geometry, the surface, and the distance between these two probes, you may calculate the electrical conductivity. So you get Seebeck coefficient electric conductivity from the LSR machine and the thermal conductivity from the LFA machine, so that you can calculate the figure of merit. This is how it looks in real life. So the thermoelectric material here is placed between the two holders, one containing a gradient heater, so heating up the sample and creating a temperature gradient in it, and two probes measuring the temperature and the voltage drop. There are a couple of options available, like multiple furnace options, a camera which allows to measure the distance between these two probes with a very high accuracy. There are options to measure, to analyze thin films in such a device with a so-called high resistance options. There are different options for the type of thermocouples used to measure the temperature gradient. And there is a so-called Harman add-on, which allows the direct measurement of the figure of merit. Let's have a look how this Harman method works. You feed electrical current to the thermoelectric material, and you measure again the voltage throughout this material. And the voltage as a function of the electrical current is plotted, and the thermoelectric voltage can be separated. We will see this later, how this is done. The thermoelectric voltage can be separated from the ohmic voltage drop, and by dividing one by the other, you get directly the figure of merit. And there is a machine, the so-called LZT meter, the Linzey's figure of merit meter, which is a combined instrument containing a laser flash analyzer and containing the features of a Seebeck and electric resistivity meter. So that you may measure all three parameters needed to calculate the figure of merit in this machine. There is a further very useful instrument for the characterization of thermoelectric materials, the so-called HCS, the Hall constant system. So you can characterize the Hall, measure the Hall constant, and from the Hall constant, the charge carrier concentration and mobility can be calculated. This plot shows that the figure of merit depends on the charge carrier concentration, and the highest figures of merits are found for charge carrier concentrations which are typical for semiconductors. So semiconductors have the highest thermal conductivity, the highest figure of merits. So thin films are a quite hot topic in the field of thermoelectric materials research for the reason that for a given chemical composition, by changing the structure, the internal structure of the material, so making a nano compound, a thin film out of it, mainly the thermal conductivity is decreased, while the Seebeck coefficient and electrical conductivity remain more or less constant. So by decreasing the thermal conductivity, you may increase the figure of merit. And this is due to the effect that there is a scattering on particle boundaries and surface boundaries, so decreasing the thermal conductivity. The instruments which are used for the characterization of thin films are the so-called thin film analyzer. It's a complete measuring platform using disposable sensors on which a thin film is deposited. Then this disposable sensor with a film on it is placed in the analyzer, and depending on the configuration of the analyzer, You can characterize the Seebeck coefficient, electric and thermal conductivity, the heat capacity, the Hall constant, charge carrier, concentration, and mobility. The thin film laser flash analyzer is an instrument dedicated to measure thermal conductivity and thermal diffusivity. These methods distinguish each other by the direction of the measurement. In the thin film analyzer, all properties are measured in the plane of the thin film, while for the thin film laser flash analyzer, the thermal diffusivity and conductivity are measured across the plane of the thin film. So complete thermoelectric generators containing these thermoelectric legs, materials, which are coupled to a device, is characterized, for example, by the TEC tester. The TEC tester allows to establish a thermal gradient throughout the generator and to measure the output power in electricity. So you may do the so-called maximum power point tracking under variable thermal load. With a TEC tester in the so-called TIM tester mode, TIM tester standing for thermal interface materials, the thermal impedance of materials may be analyzed, for example, for thermal greases and conductive pastes, which are used to build up thermoelectric generators. The laser flash analyzers may also not only be used to measure the properties, the thermal conductivity of the legs, but also of the ceramics used to build up a thermoelectric generator. And the differential scanning calorimeter is used to measure the heat capacity, which is needed to calculate the thermal conductivity from the thermal diffusivity. So for a complete measurement by the laser flash analyzers. And a DSC may also be used to characterize the thermal stability of these thermoelectric materials, but also of other chemicals like the thermoconductive pastes used to build a thermoelectric generator. So, as already said, the figure of merit depends on the charge carrier concentration and is very high for semiconductors and much less for metals because they have a very high electric conductivity and a high thermal conductivity as well, and insulators. Every material has a certain figure of merit, but the figure of merit depends on the temperature. And some materials like bismuth telluride have a maximum of the figure of merit at quite low temperatures, around 130 degrees centigrade, while others like silicon germanium compounds may have very high optimum temperatures for the figure of merit, around 1000 or 900 degrees. So let's have a look on some examples. On the left-hand side, you see the measurement of the Seebeck coefficient and the electric resistivity in red, Seebeck coefficient in blue, over temperature for a silicon germanium compound, and the measurement was done with a LSR instrument. In the beginning, we saw that the so-called Harman method, which is an option, an add-on for the LSR instrument, allows to measure the figure of merit directly without going by electric conductivity, thermal conductivity, and the Seebeck coefficient. In this example, the measurement of the figure of merit of bismuth telluride is shown. So you see the voltage, the measured voltage over time by switching on an electrical current. So when you switch an electrical current on, you get an immediate increase of the voltage, followed by a slower increase of the voltage. This is an ohmic part of the voltage increase, and this is a thermoelectric signal, so this needs more time. And by dividing the thermoelectric part by the ohmic part, so this part by this part, you get the figure of merit, in this case 0.5. Later, the current was switched off, so you get the voltage drop, the ohmic voltage drop and the thermoelectric drop. Then the current was switched on in the opposite direction, and you get the ohmic and the thermoelectric part in the inverse direction. And by switching off the current, you get again the voltage drop for the ohmic part and the thermoelectric part. And you see that the results are almost the same. The figure of merit is 0.5, 0.49 for such a measurement. In this case, it was done at room temperature. These examples show the analysis of thin films by the thin film analyzer. So I said the thin film analyzer is a complete platform to characterize thermal properties, thermophysical properties of thin films. The thin film was in this case a bismuth antimonide nanofilm of 84 nanometer thickness. And the measurement was done in a temperature range from 100 Kelvin up to 400 Kelvin. And you see the electric conductivity, the thermal conductivity, the Seebeck coefficient in green, the electric conductivity in blue, the thermal conductivity in pink, and the overall result is the figure of merit shown in yellow color. So this was a nanofilm, a very thin nanofilm of semiconducting material. The analysis can also be done on organic films, in this case a P.PSS layer of 15 micrometer thickness. And again, you find the Seebeck coefficient, the thermal conductivity, the electric conductivity, and the figure of merit, the overall result. The measurements are done on the disposable sensors on which the thin film has to be deposited. Here you see an example of a gold or of a titanium thin film on such a disposable sensor. And you see the results of a 100 nanometer gold and titanium layer. So I want to stress out one point, which is here the thermal conductivity represented in blue. For gold of this thin layer, it's 160 watt per meter Kelvin. For bulk material, the thermal conductivity is 300 watt per meter and Kelvin. So showing that thin layers have different thermophysical properties than bulk materials. And thus, you may increase the figure of merit by having a thin layer which has a reduced thermal conductivity. In the second example, you see the thermoelectric analysis of a titanium layer. Again, here in blue, the thermal conductivity of this layer, which is around 10 watt per meter and Kelvin, while bulk material, bulk titanium has a thermal conductivity of 22 watt per meter and Kelvin. So more than 2 times more the thermal conductivity than this thin layer of 100 nanometer. And a last example, a full characterization of 2 materials, P and N-type bismuth telluride containing also selenium or antimony by laser flash analyzer. So this is a representation of the thermal diffusivity over temperature. The specific heat capacity has been measured in the same temperature range. The density is known. So you may calculate the thermal conductivity by multiplying the diffusivity with a specific heat and the, the density. This has been done by laser flash analyzers, specific heat by DSC machine. The electric resistivity and the Seebeck coefficient have been measured by the Linsa Seebeck and resistivity analyzer, and by doing the calculation, Seebeck coefficient squared multiplied with the electric resistivity, electric conductivity divided by the thermal conductivity gives the figure of merit of these two materials. So this is the presentation I wanted to show to you.